In the last video, we said that we can't solve exponential equations with more than 2 terms unless we get very lucky. So this is one way that we can get very lucky. Here's what it looks like. This is another place where we can pretend that we have a polynomial on our hands. So in this equation, this certainly doesn't look like a polynomial. We've got all these exponential expressions, and these two have got different bases. What on earth could we possibly do with that? Well, we notice that these bases are different, but not unrelated. 4 is 2 squared. So 4 to the x is 2 squared to the x. That's 2 to the 2x, which we could also write as 2 to the x squared. Ah, there it is. This is actually a quadratic in 2 to the x. Right, so we'll have two to the x squared plus 4 equals 5 times 2 to the x. Collect all the terms on one side because we're solving a polynomial. We've got 2 to the x squared minus 5 times 2 to the x plus 4 equals 0. And now we can factor this. We're thinking that we're factoring u squared minus 5u plus 4. Well, that's a quadratic. Leading coefficient is 1, so we can use the shortcut. Two numbers whose sum is -5, whose product is +4. We want -1 and -4. So our original equation will have 2 to the x minus 1 times 2 to the x minus 4 equals 0. Now we've got something factored equal to 0. One of the factors must be 0. Either 2 to the x minus 1 is 0, that is 2 to the x is 1, or 2 to the x minus 4 is 0, which would be 2 to the x equals 4. At this point, we could do this by taking the log of both sides, but we know that 2 to the 0 equals 1. And we know that 2 squared equals 4. So we have two solutions, x equals 0 and x equals 2. Let's check that in the original equation and make sure that this really worked, because we made this very strange move. If we have 4 to the 0 plus 4, does that equal 5 times 2 to the 0? Well, this is 1 plus 4 equals 5. That's true. 4 squared plus 4, does that equal 5 times 2 squared? Well, this is 16 plus 4 equals 5 times 4 is 20. That is also a solution. So that really did work for us. Pretending that this was a polynomial really did work for us. Notice that in order to spot that this was a polynomial, in order to treat this as a polynomial, we had to mess around with the exponents, right? We had to mess around with this in order to spot that this was a polynomial. Sometimes we have to mess around a little bit more, as in the next example. So here we have an equation with exponential expressions, and we notice that they have the same bases. Right? We notice that each of these bases is a 3. That causes us to hope that we might be able to write this as a polynomial. And in order to do that, we need to rewrite one of these exponents as some constant times the other one. And looking at the x's, right, I think that I would like to have this exponent be 2 times this exponent, right? Because that's the best way to go from an x to a 2x. But if I take 2 times x plus 1, that's 2x plus 2, which is not 2x plus 3. So I need to do something to my exponents. I can either make them bigger or I can make them smaller. How? If I multiply both sides of this equation by some power of 3, right, I would like to take 3 to some power and multiply that by both sides of this equation. And that'll give me, well, when I multiply powers of the same base, I add the exponents. I'll have 3 to the 2x plus k. I'll have 3 to the 2x plus 3 plus k minus 3 to the x plus 1 plus k minus 4 times 3 to the k equals 0. And this will just be a constant, right? Because I'm going to pick some number. I want to get 2 times x plus 1 plus k to equal 2x plus 3 plus k. Well, let's beat that with an algebra hammer and see if the answer falls out. All right, see if we can figure out what k is going to have to be. So 2x plus 2 plus 2k equals 2x plus 3 plus k. Well, the x terms cancel out. 2 plus 2k is 3 plus k. Well, subtract k, subtract 2, and we get k equals 1. We just have to multiply both sides by 3. So let's see what that does. If we take 3 times 3 to the 2x plus 3 minus 3 to the x plus 1 minus 4. On the right, we'll just have 3 times 0 is still 0. That's why we didn't fuss with that earlier. Well, that adds 1 to each exponent. So we have 3 to the 2x plus 4 minus 3 to the x plus 2 minus 12 equals 0. Okay, but 3 to the 2x plus 4 is 3 to the 2 times x plus 2. So that's 3 to the x plus 2 squared. 3 to the x plus 2 is going to be effectively my variable here. So I'll have 3 to the x plus 2 squared minus 3 to the x plus 2 minus 12 equals 0. I'm thinking that I'm factoring u squared minus u minus 12. That's quadratic, leading coefficient 1. I need two numbers whose product is negative 12 and whose sum is negative 1. So that's going to factor as u minus 4 times u plus 3, right? We're going to have 3 to the x plus 2 minus 4 times 3 to the x plus 2 plus 3 equals 0. So one of those factors is 0. That means either 3 to the x plus 2 equals 4, or 3 to the x plus 2 equals negative 3. Now this one can't happen. Why not? Because exponential expressions are always positive. This one we can't do by trial and error, but we can do using the log. X plus 2 is the log base 3 of 4. So x is negative 2 plus the log base 3 of 4, which we could write as negative 2 plus the log of 4 over the log of 3. As a decimal approximation, x is about, well, negative 2 plus the log of 4 over the log of 3. X is about negative 0.738. We can actually check that in our original equation. I'm going to just store that in x. Negative 0.738 stored in x. Enter that in our original equation. 3 to the 2x plus 3 minus 3 to the x plus 1 minus 4, and that really is very close to 0. Right? That number that we found really is rounded a solution to our original equation.